Hi folks, in this lecture we're going to take a look at log plots. So semi-log plots and then natural log plots. So often, as we've seen, a scientist is usually conducting an experiment, or when a scientist conducts an experiment, he's changing the input and measuring the output, like what's happened when I change this, what happens to that. And very often we'll get a curve that looks like this. But unfortunately, as we saw last semester, I'll give a quick review in the next couple of slides as well, but there's several curves that look like this. So this isn't just the shape of the curve itself doesn't tell you what the function is. You have to do a bit of analysis. So it's very risky to presume, say, oh, looks exponential, so therefore it is exponential. This curve, I'm pretty sure that curve is actually quadratic. So just taking a look at some quadratic functions, there's another one. Any of these kind of situations would be quadratic. Anything to do with area is quadratic. Wave height versus power. So the power is proportional to the wave height squared. Same here. Etc. Or it could be a cubic function. Cubic functions look like that. And here's some examples of cubic functions. We examined these in more detail in semester 2. Exponential functions. And again, it's got the same general shape of curve. Here's some examples of exponential functions. So any of those three types could lead to a curve that looks like this, or make it look a little bit more professional, like that. So we have to do a bit of analysis first, and that's what we're going to kind of look at in this lecture. So how do we determine if a function is exponential? So just like I was saying, just drawing a graph is not conclusive. So this curve, as I said, could be growth, exponential growth, could be quadratic, could be cubic. And this one here could be exponential decay. It also could be the left-hand side of a quadratic or a cubic, or it also could be a reciprocal curve either. So again, the main point is can't tell what a function is just by looking at its curve, unless it's a straight line. So we're going to take a look now at the first method. So in this lecture, we're going to cover two methods of determining if a function is exponential. First method, using semi-log graph. So most of you won't have seen a semi-log plot before, or a semi-log graph. So one axis is logarithmic and the other axis is linear. So used quite a lot where we suspect data has an exponential relationship and we want to prove it, or if we know it's got an exponential relationship, or generally if one or more of the variables cover a large range of values. Like when we were looking at the decibel scale, it goes from 20 micropascals to 200 million micropascals. If you're trying to deal with a large scale like that, often a log curve or a semi-log curve will help you out. So a log linear, it's kind of the y first and then the x. So the log linear is the y-axis is logarithmic, the x-axis is linear. And these are the ones we'll be looking at. Then there's linear log, which looks like this. And there's also then log, which looks like that. But we're going to be using these ones here. log linear plots. So here guys, we've got log linear paper on the right hand side. There's 2 cycles. You can see it goes from 1 to 10. And then, so each of these is a cycle. And they represent, say this could be 10 to the power of 0, and then the next cycle up will be 10 to the power of 1, and the next cycle. So kind of once you choose a starting cycle, then they increase as you go upwards. So what that means, guys, I'll just give a quick explanation, is here, I'll just actually explain it here, I've written it out. The y-axis is logarithmic. So the spacing here, guys, even though it's labeled 1 to 10, they're actually spaced out in proportion to the log of the number. So if you get the log of 2, that's what that gap represents. That's the log of 3, sorry. The log of 2 is there. So here, if I've got 2 cycles, as I said, this is the 10 to the power of 0 cycle. So this value here would be 1 by 10 to the power of 0, which is 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10. And this 10, guys, represents the end of the old cycle and the beginning of the next cycle. So now this value here, this is now the 10 to the power of 1 cycle. So this value isn't 2, it's actually 2 by 10 to the power of 1, which is 20. 3 by 10 to the power of 1, 30, 40, 50, 60, 70. So any values between 1 and 10 would be registered here. Any values between 10 and 100 in this cycle, then the next cycle it will go 100, 200, 300, etc., etc. So the x-axis is linear. We still just divide this off. Probably best using a ruler and divide it off linearly. Remember, guys, to label your axes correctly. Coins in your pockets, not 4, 3, either 1, 2, 5, 10, 20, 50, 100. Those are your correct intervals. So don't, guys, submit graphs. Well, if you lose marks if you do, but if you kind of have 4, 8, 12, even if the data is given to you like that, if you write your axes like that, guys, you're going to lose marks, because in science your intervals must be 1, 2, 5, 10, 20, 50, 100, 200, 1000, 500, 1000, etc. So just watch out for that, guys, don't get caught out. X-axis is linear, as I said, and then coordinates are marked as normal. So 3, 6, go across 3 and up 6. 5, 30. Now here we're dealing with 30, so it's up in the next cycle, the 10 to the power of 1 cycle, and there's 530. So we look at a couple of examples and hopefully it'll make a bit more sense once you see a few. You guys will be doing these as well as part of your journal. So how many cycles? We'll take a look at this by example, but really what you do is you're just trying to figure out how many 10 to the power hours of do I need to cover, or does my data cover. So write your lowest data value in scientific notation and your biggest data value in scientific notation. So I'll explain it in an example, probably it'll be a little bit better. So here I've got 2 cycle paper. And here I'm just showing, guys, you could use different, if the data necessitated. Here's the 10 to the power of minus 3 cycle. So the next cycle up, guys, must be the 10 to the minus 2. Once you figure the pattern, it's the same all the time. The next cycle up would be 0.1, 0.2, 0.3, 0.4, and then we'd be back up to the 10 to the power of 0 cycle, which was on the previous slide. So your data will determine how many cycles you need. And if you need to interpolate your data back, make sure you include an extra cycle. So just say, often guys, I'll be asking you for the initial conditions. Where does the line cut the vertical axis? You need to make sure, if that's what's required, that you've included an extra cycle at the bottom. So it would have been better in this case to use 3 cycle paper in order to capture where my line, where my curve cuts the vertical axis, because I'm looking for this point here down at the very bottom, and I've no information about what's going on down there. So watch out for that, guys. Try not to get trapped by that. I will be looking for that where does the line cut the y-intercept quite a bit, because that's part of our analysis, which we'll look at in the next lecture. So now here's a typical example. I think this was taken from an exam. So if we just plot it as normal, it looks exponential, but as I said, that's not verification in itself. So what we do is first, how many cycles do we need? So here, guys, I'm going from 2.5 by 10 to the power of 0. That's my lowest value, up as far as 8.19 by 10 to the power of 1. So I need to accommodate this cycle and this cycle. So in this case, I only need 2 cycles. Sometimes, like I said, it's a good idea to add an extra cycle if we're going to be doing any analysis, just to make sure you can capture where your line cuts the vertical axis. So here's 2 cycle paper. Mark off each axis. So there's the linear axis. And there's my 10 to the power of 0 cycle. Going in. And now 20, this is my 10 to the power of 1 cycle. So I have enough here to capture all the data, because the highest value is 81.9, the lowest value is 2.5. Mark in my points. And then using a ruler, draw a best fit line. And usually, guys, they won't be as nice as this, so don't force the points. Make sure, I'll have designed the data that it won't be a perfect, the dots won't line up perfectly. It's because I want you to do a bit of analysis and try and figure out what's the best line that represents these points. So don't be surprised if your points might be a little bit more like this when you're doing the journal. That's perfectly natural. So once you get a straight line, guys, because often if the data wasn't exponential, we wouldn't get this straight line. So because we've got a straight line, using a log, semi-log paper, we've now verified that the input and the log of y are proportional. A straight line indicates proportionality. So if this is true, if we raised both sides as a power on 10 to kill the log, then this statement here is true. So y is proportional to 10 to the power of x. Now it's very important, guys, this is exponential. When we say exponential, we're talking about the variable is in the power. Don't expect e is exponential because it's always written with a power. This is exponential. So it doesn't have to have this base of e to be exponential. Any base with a variable power is an exponential function. So here's just another example. Here's the data. Sorry, I probably went through that a little bit quick. So main thing, we're going from 22 up to 6,000. Remember, this is a 10 to the power of 1 value, 10 to the power of 3. Here is 10 to the power of 2. So I'm going to have to accommodate at least 3 cycles. Use this graph to determine the initial conditions. That would generally have me going for 4 cycles. Now, in this case, guys, I actually just went for 3 cycles because it loses clarity when I'm using PowerPoint and stuff, so I felt 3 cycles will serve me well enough. So here's my lowest value. Here's my largest value. This is just what I was saying on the earlier previous slide. So these are the cycles I need to accommodate. So I need at least 3 cycle paper. So that's what I've used. You know, often in your case, it might be better to choose 4 cycle, but it gets very cramped when I'm trying to explain it on a slide. Mark in my axes. So again, guys, I need to have lowest cycle is 10 to the power of 1. This will accommodate all values up to 100. Here's all my 10 to the power of 2 cycle values. And then these are all my 10 to the power of 3 cycles. So these are the 3 cycles. 10 to the power of 3, 10 to the power of 2, and 10 to the power of 1. Now you don't need to write in these brackets like I've written them, but it's just to kind of explain what's going on. So here, this first cycle represents all values between 10 and 100. Next cycle, all values between 100 and 1000. And the last cycle, all values between 1000 and 10,000. So now we mark in our coordinates from here. And join the dots. Now, one thing, guys, that's very important is we're asked for the initial conditions. Nearly always it makes sense to extrapolate the line. So extrapolate the line just literally means get a ruler and find out, it's kind of you're finding more than you have from your data set up here. So we're kind of saying, well, what happened at t is equal to 0? We've no information about that from our table, but we can use extrapolation to figure that out. And now the question asks what the initial conditions were. It cuts the y-axis at y is equal to 10. So x is equal to 0. In this case, t is equal to 0. And n is equal to 10. Those are our initial conditions. So that's the main point, guys. Really, in the first kind of lecture, I'm really just getting you used to the idea of drawing graphs with these. And then if you get a straight line, you know, you can verify that it is an exponential function we're dealing with. We can also then find the initial conditions. In the next lecture, we'll be using these skills to analyze and then determine, well, what's the nature of the function that produced this data. So this is just an example for you guys to try. You can see there's lots of cycles to be accommodated. We have to go from 10 to the power 2 to 10 to the minus 3. So that means I need at least 5 cycles. Now you'll find all the different cycles of paper on Moodle. So just take a look and you'll see there's one, I think, through to 5 cycle paper. I generally don't do too much stuff beyond 5 cycle because it just gets very cramped. So here's one, guys, if you want to try it. Again, you'll have ones in the journal as well. But any questions like these, guys, that appear in lectures would be very typical of what would appear in an exam situation at the end of the semester. So I leave it up to you. So that, guys, is the first method. So that kind of brings us to the end of method 1, and now we're going to take a look at method 2, which is maybe preferred for several reasons, as you'll see yourselves as we work our way through the material. So in this case, guys, we're going to use normal graph paper, but we're going to get the natural log of our y value. So I'll explain why we do that in a slide or two. So this is what we actually want to verify. We want to say, well, is our data exponential? Is my output y proportional to e to the power of x? Because then if I get a straight line, so essentially, guys, what I'm going to do is I'm going to plot these. So you'll be given a bunch of data. Here's x, just like before. 1, 2, 3, 4, 5, 10, 20, 50, you know, something like that. We could just plot our y values and then get e to the power of x. So we could raise, instead of writing 1, we could get e to the power of 1, e to the power of 2, e to the power of 3, e to the power of 4, e to the power of 5. And then plot this value versus that. And we get a straight line. And if we get a straight line, that verifies that y is proportional to e to the power of x. If we don't get a straight line, then that would suggest, so say you just draw your graph. And you suspect it's exponential. If, say, when you plotted them, your data actually went like this. So it's very obvious that a straight line doesn't suitably plot the curve. So if your data doesn't produce a straight line, that would suggest that this is not exponential. So that's what we're trying to do. We're trying to establish, is the function exponential? So I'm going to clear all of this. So that's our general idea. We want to plot e to the power of x versus y. If we get a straight line, we've verified that this is true. Y is proportional to e to the power of x. The big problem with doing this, guys, is e to the power of x gets really big really quickly. So if you're looking for e to the power of, say, 20, the values just get huge. Just getting a calculator. E to the power of 20 is 485 million. So you can see the values get very big. So to try and counteract this, guys, if we, like I said, the problem with plotting these is that the e to the power of x gets way too big way too quickly. But however, we can take a little sidestep, get the natural log of both sides. Now we'll have the natural log of y. A proportional sign, guys, you can just treat as an equal sign. You just do the same thing to both sides and everything is okay. On the right hand side, those will cancel out. So now we'll have the natural log of y is proportional to x. So these are the same statement. The top one is just an exponential statement. The bottom one is saying the exact same thing, but in terms of logs. So if we now draw a graph, of natural log of y, ln y, versus x, and we get a straight line. This then verifies that this statement is true. From what I said earlier, if this statement is true, then that follows that the original statement is also true, because they're the same thing. They're both saying the same thing. So, say we have a graph, or we have some data, we suspect it's exponential. We then plot natural log of y, versus x, and we get a straight line. If the slope of that straight line is positive, guys, the straight line verifies your data is exponential. The fact that it's a positive slope verifies that you're looking at exponential growth. So the positive slope and the straight line give us the two different parts, exponential and growth. Conversely, if we're looking at exponential decay, we plot ln y versus x. We get a straight line, but now it's a downhill slope. So a negative slope, again straight line, verifies that it's exponential. If it's negative, that verifies we're looking at decay. So here's the data from the previous slides when we were looking at semi-log plots. If we plot it just as before, it looks exponential but not conclusive. So what we do now, guys, is we actually create a new line. You just create a new row in your table, and we get the natural log of each value, and we write it in here. Label each axis and mark in each coordinate. So here's my axes, natural log of y and x, and now I'm marking in 0.92. Then this 2 with 1.41, that's that point. 3, 1.9. So those are my coordinates that I'm marking in. Use a ruler, and now we can see that the natural log, we've got a straight line, so the natural log of y is proportional to x, so therefore y is proportional to e to the power of x. So that verifies the data is exponential. We can work out our initial conditions if we need to as well. That requires, though, just that value here, be careful there, guys, that's not y, remember that's the ln of y. So in this case it could be 0.4. In order to get y, we have to do a little bit of maths, so just be careful. That's how we find the initial conditions, but you need to do a little bit of maths to actually figure out what the y value is. We'll see this in the next lecture when we start delving into the analysis. I'm sure you're looking forward to that. So here's the same data from before, but now we're just going to verify it using this new technique, plotting the ln of our output versus our input. So first thing, create a new table showing this new line. We already have these two in the table above. Plot the graph and then determine what were the initial conditions. So it's very hard to get any information from that curve, just plotting n versus t. But now again, here's my points. 4, 3.1. etc. Then this point here, just I won't write them all in obviously because it gets very tedious. So there's my points then. Get a ruler, join your dots, and then we want to work out what were the initial conditions. So that's actually at 2.3, so lny is equal to 2.3. So this point of intersection is x is 0, 2.3. The only difference though is that's x, and this is the lny. So we want to actually work back with what's the y value. We raise both sides as a power on e. When we do that to the left hand side, we just get y is equal to e to the power of 2.3. And that gives us 9.9, which is close enough. It's actually 9.974. So we'll just say it's 10. And that kind of confirms what we got in the previous example. Generally though, guys, these plots are much easier to analyze. First of all, because you're using normal graph paper. And the maths as well is a good bit more straightforward. Here's just the other example again, but you got asking you to use this new method, plotting ln of c versus t. See if you get a straight line and try and determine, well, what was the initial concentration of the drug. So this is a decay example. So that, guys, finishes us up for here. So thanks for listening, and we will in the next lecture then start taking a look at the analysis side of these plots that we've just created. So thanks again, and we shall chat again soon.